These bottles do exactly what their name implies. They accumulate. What is it they accumulate? Fluid volume under pressure. These are the holding tanks, so to speak, for the hydraulic fluid that's the lifeblood of your control system. We use two sizes in Sedco Forex systems, 11 and 15-gallon capacities. You know where they are. The main accumulator bottles are skid-mounted at the hydraulic power unit. Then, of course, there are the stack-mounted accumulators. We use these as a power source right at the stack for more immediate response times. This program addresses two subjects: bladder replacement, a very simple operation, and proper pre-charge levels. This is critical, of course. We'll use some math to ensure you properly pre-charge your subsea accumulators. As you probably know, hydrostatic pressure and sometimes temperature at the sea bottom determines your pre-charge pressure. In fact, we've included a workbook with this program to help you through these critical calculations. If you don't have it handy, stop the tape and locate your workbook. First, let's assume you suspect a faulty bladder somewhere. We've got to pinpoint that bottle. First, you have to remove hydraulic pressure to your accumulators. Then, drain them back to tank. With the subsea accumulators, for example, you do that by placing the pod selector valve in the center position and opening the accumulator isolator. Make sure the bottles are completely empty of hydraulic fluid. You can crack a fitting in one of your manifold lines to be sure no pressure remains in your subsea bottles. Now you can check the pre-charge on each bottle. If a bladder has burst, the pre-charge will be gone when you check the bottle. If it's merely leaked, then there may be some pre-charge left. Perhaps it's a faulty stem or core, or maybe there's a pinhole somewhere around the bladder. If all the bottles are equally low, it may be that a change in surface temperature has caused the problem. If the stem is leaking, you have several options. First, try tightening the core. Maybe it's just loose. If it still leaks, you can try replacing the core. That should solve the problem. Additionally, if you don't have any of these seal caps, you might want to get some. They actually have a rubber seal inside that can hold your pre-charge if the stem goes bad. Screw it down tightly. If after all this the bottle still won't hold a pre-charge, it probably has a leaking bladder. The bladder will need to be replaced. In this case, you'll have to remove the bottle from the skid and take it to your work area. There are a few rigs out there with top-loading bladders. If that's the case, you'll be able to replace the bladder without removing the bottle from the skid. If you've worked on more than one rig, you've discovered any number of designs in the Accumilator room. None of them seem to facilitate maintenance of an accumulator, like here, or here. You know the best way to lift it off the skid and get it to your work area. Just remember one thought: heavy. The manufacturer lists the weight of an 11-gallon bottle at over 300 pounds. Get someone to lend you a hand. You'll save wear and tear on your body. And when you lift, lift with your legs, not your back. Bladder replacement won't take long, and your rig manual details the step-by-step process. We'd like to stress some important points, however, for you to remember as you go along. Once you've disassembled the bottle and you're left with an empty shell, do a visual inspection of the inside of the bottle. Look for any foreign matter that might have caused a puncture, or bacterial growth that may have caused premature wear. Clean the edges of the holes if there's any sign of scale or buildup. When you locate a new bladder, remember, it has a maximum pressure rating just as the bottles do. Make sure you have the properly rated bladder of the correct size for your system. Pour a little oil into the accumulator shell so the bladder doesn't stick to the bottle wall. This will ease assembly for you. Use hydraulic oil a low-grade oil that's not petroleum-based, or your hydraulic concentrate. Whenever you handle the pull rod and bladder stem, be sure not to bend the stem. Always make sure you get a straight pull. And remember, there are only 5 threads on the stem. No need to get over-enthusiastic with the lock nut when you replace it. As you tighten the lock nut, make sure the bladder doesn't twist inside the bottle. During reassembly, do a quick inspection of the plug assembly, especially the poppet and spring. Just make sure the spring isn't broken and it allows the poppet to seat fully. If the poppet doesn't seat all the way, the bladder could get pinched between the poppet and plug and probably burst. And when you're finished, don't forget the valve guard. Be sure and have the valve guard in place whenever you transport the bottle. Replace the bottle on the skid and you're ready to pre-charge. We'll spend a minute on the pre-charge procedure and then we'll get to the nitty-gritty, those critical pre-charge calculations. Remove the valve guard from the bottle and attach a gauge and charging assembly. Don't over-torque the swivel nut, just provide enough torque to seat the brass gasket. Make sure the bleeder valve and regulator are closed and the T-handle is all the way up before fitting it to the accumulator. Attach the hose end to a nitrogen bottle. Open the nitrogen bottle slowly. Then, increase the regulator pressure setting until the gauge reaches the proper accumulator precharge level. Screw the T-handle all the way in, and the precharge will flow into the bottle. You'll have to shut off the nitrogen flow periodically to check your pressure level on the gauge. Then open it to continue flow. It'll take a while to fill an empty bladder with a fully charged nitrogen bottle. When the process is complete, close the bottle first, and then return to the accumulator one more time. Screw the T-handle on the charging assembly out until it stops. Open the bleeder valve, and the nitrogen trapped in the hose will be released.
Done. Say we're done.
Take off the gauge and charging assembly. Replace the seal cap and check for leaks. Then replace the protector cap. The pre-charge process is complete. So, what about those accumulator pre-charge pressures? Well, the fact is, there's no longer any established set of hard and fast rules, mutually accepted worldwide, that tell us what the pre-charge pressure should be. The guidelines and requirements vary from one regulatory body to the next, and some vendors show different minimum operating pressure requirements for their different pieces of preventer equipment. With that in mind, we'll leave it up to you. Make certain you're meeting SEDCO 4X policy or the rules of the regulatory body governing the waters you're currently working in. Use whichever is more stringent. Now, for surface accumulators, you simply charge each bottle to the required pre-charge pressure. The subsea accumulators are a slightly different story. We still want the same pre-charge as the surface accumulators, but subsea accumulators have to overcome hydrostatic pressure of the seawater to operate or function. So, charge subsea accumulators to surface pre-charge plus hydrostatic pressure. Hydrostatic pressure, of course, is the pressure, expressed in pounds per square inch, created by the weight of seawater at a given depth. This cube represents a cubic foot of salt water. It weighs 64 pounds. Each face of this cubic foot is 144 square inches. Using the top face, we can imagine 144 columns of water with a square inch surface at top and bottom. One column weighs 0.445 pounds. That's 64 pounds divided by 144 columns. Of course, the weight of each column acts over the square-inch surface at the bottom. So, hydrostatic pressure is 0.445 psi per foot of seawater. Each foot you go deeper adds another 0.445 psi hydrostatic pressure. Let's do an example. Say your surface precharge is 1,000 psi. You're drilling in 600 feet of water. You'll charge your subsea accumulators to 1,000 plus hydrostatic plus atmospheric pressure of 14.7 psi. We tend to forget about atmospheric pressure because we never think of air as weighing anything. But actually, a 1-inch column of air from the surface to the top of our atmosphere, about 10 miles high, weighs 14.7 pounds. So to be technically correct, you have to add that 14.7 to all your calculations. Back to our example. In this case, hydrostatic equals 0.445 times 600 plus 14.7. That's 282 psia, making your precharge 282 plus 1,000, or 1,282 psia. It's that simple. What if there's a temperature difference between the surface and subsea? This is likely to occur in deep-water drilling operations. For instance, say it's 80 degrees Fahrenheit on the surface, but only 30 degrees subsea. Cold naturally causes gas to contract, decreasing the pressure in any sealed container. So if you charged your stack accumulators on the surface at a warm temperature, then sent them subsea to a cold temperature, you'd have problems. Forgetting hydrostatic pressure for a moment, the lower temperature alone would cause the nitrogen pressure to be much less. What would the result of that be? The equivalent of a low precharge pressure. You'd get the last drop of fluid out of the bottle at a reduced pressure, a pressure that might not be high enough to operate functions. To calculate the proper precharge with a temperature difference from subsea to surface, the specific volume method has been developed. Specific volume is the cubic feet of gas occupied per pound of gas at a given pressure, volume per weight. Nitrogen has a specific volume at a given pressure and temperature. This specific volume changes with effective changes in pressure or temperature. The specific volume method uses actual subsea conditions of pressure and temperature to derive a specific volume. Then, using that same specific volume with the increased surface temperature, we're able to calculate the required surface precharge. This surface precharge will compensate for the loss of pressure due to reduced temperature at the seabed. This worksheet will help you understand the calculations and find the proper precharge. P1 is psia nitrogen precharge pressure at the seabed. T1 is the subsea temperature. V bar 1 is the designation for specific volume at the appropriate subsea temperature and pressure. P1 must be calculated. It's the same simple formula we mentioned earlier. Surface precharge plus hydrostatic. Hydrostatic, remember, equals 0.445 times the water depth. For purposes of the specific volume method, add 14.7 to find absolute pressure. We now have all the numbers we need to find V bar 1, specific volume. You'll find this value using this chart. It gives the specific volume of nitrogen for temperatures ranging from 30 to 100 degrees Fahrenheit and 200 to 10,000 psia. There are gaps between the listed pressures and temperatures. For values falling between the listed numbers, you'll have to interpolate. So, what do we have once we've filled in the top part of this worksheet? We have the precharge required subsea at a given water depth and temperature. Considering the precharge and subsea temperature, we've been able to calculate specific volume. But what do we precharge to at the surface before we send the stack subsea? In light of an extreme temperature difference, you realize that charging to surface precharge plus hydrostatic isn't going to be enough. Here's where specific volume acts as a constant. The second half of the worksheet allows us to find the surface precharge for the subsea accumulators. By using the same value for specific volume that we derived from the subsea conditions, we're able to use this chart and interpolate the required surface precharge pressure based on a new temperature, the temperature on the surface. On the worksheet, notice V bar 1 equals V bar 2. We know what T2 is. Given temperature and specific volume, then, we can determine our third variable. That's P2, the required surface precharge in PSIA. Subtract 14.7 and you'll have your gauge pressure reading. A detailed example, including an explanation of interpolation, is given in the accompanying workbook. There's a regulatory agency out there somewhere that's going to tell you how much usable fluid you must have in your system. If you're in North America, for example, that agency is MMS, Minerals Management Service. In the UK, it's DEN, Department of Energy. In Norwegian waters, it's the NPD, Norwegian Petroleum Directorate. MMS currently requires that you have 1.5 times the volume necessary to close all BOP equipment units. After closing all functions, the accumulator system must be left with a minimum pressure of 203 psi above the precharge pressure. So, say you've got 2 annulars that require 40 gallons each to close, and it takes another 20 gallons apiece to close your 4 rams. That's a total of 160 gallons to close all functions. 1.5 times that is 240 gallons. You must have 240 gallons of usable fluid in your system. Let's determine how much usable fluid is in one surface accumulator bottle in a typical system. Say we're using 11-gallon bottles. We'll fill one with 11 gallons of fluid. Let's put an empty bladder in there. It displaces about 1 gallon of that fluid, leaving us an actual fluid capacity of 10 gallons. By the same token, when the bladder is fully charged with nitrogen, displacing all fluid, the gas also occupies a volume of about 10 gallons. Let's do an example. Here's a bottle with a bladder pre-charged to 1,000 psi. We'll charge the bottle with fluid now to 3,000 psi. The gas inside the bladder becomes compressed as fluid enters the bottle. Now the fluid is occupying a certain volume, while the nitrogen is occupying less. But the total volume of fluid and gas still equals 10 gallons. Let's determine the volume of gas with 3,000 psi in the bottle. If the fluid is pushing up on the bladder with 3,000 psi, then the gas is pushing back with the same 3,000 psi. For every action, there's an equal and opposite reaction, Newton's third law. Boyle's gas law says that pressure is inversely proportional to the volume, assuming a constant temperature. That is, if pressure increases, volume decreases proportionately. The formula you've probably all seen is P1 times V1 equals P2 times V2. In this case, our P1 V1 situation will be 1,000 psi P1 times 10 gallons V1 equals 3,000 psi P2 times the volume of gas at 3,000 psi V2. Solving the equation, you see the new volume is 3.33 gallons of nitrogen. 10 gallons minus 3.33 of gas means there's 6.67 total gallons of fluid at 3,000 psi. How much of that fluid is usable? Well, remember, MMS says the pressure must be at least 203 psi above the precharge after all functions have been closed. That tells us the last drop of usable fluid must be at least 1,203 psi. So, we know P3 is 1,203 psi. Let's use P1 and V1 again. 1,000 times 10 equals 1,203 times V3, the volume of gas at 1,203 psi. Solving the equation, we discover that the bottle contains 8.3 gallons of nitrogen at 1,203 psi. That leaves space for 1.7 gallons of fluid. Now you've got all the information you need to calculate usable fluid. Fully charged at 3,000 psi, there's 6.67 gallons of fluid. At a pressure of 1,203 psi, there's still 1.7 gallons left in the bottle. 6.67 minus 1.7 equals 4.97 gallons of usable fluid per bottle. Why is that 1.7 gallons unusable? Let's look back to our original values when the bottle was empty of fluid. The pressure in the bottle was 1,000 psi. That means the last drop out would be at 1,000 psi. As we've already stated, MMS requires the last drop of usable fluid to be at least 1,203 psi. So anything less than 1,203 is unusable. In our illustration, we said our system would require 160 gallons to close all functions. MMS requires 1.5 times that, 240 gallons, of usable fluid in the system. We said there's 4.97 usable gallons per bottle. That's about 49 bottles to carry 240 gallons of usable fluid. So, that's the video version of calculating precharges and usable volumes. The detailed explanations are found in the enclosed workbook. Use the workbook and view this tape again if necessary. A lengthy conclusion at this point isn't necessary. You know what can happen if you don't have enough fluid to close your blowout preventers. Take the time to do the proper precharge and volume calculations.